Okay, so let's go back to the unit on projectile motion first. Let's go back to that. What were we doing in projectile motion? So let's say
Projectile motion was simply gravity and
yeah, study of it has to do with gravity, right? So G is always there. As you notice, with projectile motion, the acceleration was always G, right? Because in order for something to be a projectile, the only force that is acting on it is the force of gravity. Okay, so it can't have a self-propelling device like an engine or a motor. Okay, so let's say that if I were to stand on a very tall tower, like remember in projectile motion, we were looking at, I'm standing on top of a cliff. Okay. And then if this is a cliff, and I shoot something, I'm going to call it V1, I shoot something along the horizontal. What is going to happen to that projectile? So here it is. I am on this flat earth for 8 kilometers. It's flat, right? Yep. And then I stand on the very top of the very tall tower. Why tall? Why does it have to be a cliff? Because I don't want anything to get in the way. Because that IG building, if I shoot a projectile along the x-axis, that projectile is going to hit the wall, right? So I want to make sure that nothing gets in my way, so I'm going to go on top of Mount Everest. And I'm going to, again, ignore the drag coefficient of the air. You know that air gets thinner as you go higher, and that the G gets less as you go higher, right, from the surface of the Earth. Yep. So we're going to ignore all that. But we'll assume that the G is pretty constant. G is still there, and that's the only thing working. Okay, so I shoot a projectile along the X. What is going to happen to that projectile eventually?
It will have an impact.
It curves down, right? So eventually it hits the ground somewhere. Even if you take a gun and with a very fast bullet, it's still going to hit the ground somewhere. So eventually this is going to eventually curve down because of G and hit somewhere here. What if I want to go farther? Let's say I want to go and land here. What do I have to do to my V1?
You have to either increase your V1x or you have to increase your height.
That's to increase the angle, right? Maximize the range is what? What is the angle of maximum range?
45 degrees.
45 degrees. So those are the things. But I'm not going to change my angle. I'm just going to go along the X. So just the V1 of X. So the only way you could actually get more range is to make it go faster. But okay, so you go faster and then it lands right here. But I want to make it so fast. What if I make it really, 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 really fast? You just keep going farther and farther and farther. But why is it that I'm going like this and eventually that bullet could return behind me? Is that possible?
Theoretically.
And why would that be possible? Okay, why does it curve? So you know that the projectile curves. Why?
Because of the curvature of the Earth.
Due to, no, not that. Yeah, the Earth curves, yes.
Yeah.
But why does it curve? Why does it have to follow the curvature of the Earth?
Because that's gravity will pull it towards the Earth.
That's right. There's that force, right? It always acts on that vertical component. So it's always going to be pulling it towards the center of that planet. So it's going to curve due to the FG, right? And that FG will make it go down with an acceleration of 1g. But if you were to give it enough V1 along the X we're talking about here, with enough V1, that projectile can actually become an object that can actually orbit that planet. It can become a satellite given enough speed. That's it. So it is actually possible. You go up very, very high. If you can take a rocket that is very, very fast. That's what that is, by the way, rockets. That's all it does. right? So they launch a rocket, and then eventually it will go up and up and up, and eventually that rocket will start to fall. You guys know it's falling along the way, right?
Yeah.
But as the fuel gets used up, that is actually going to decrease that speed. Why would it decrease in speed? So when you launch a rocket off Cape Canaveral, they aim the rocket vertically straight up. So the rocket goes up. Why? Because you want to get off the ground, right? So they launch it, but eventually that rocket is going to start to fall down.
Yeah.
And when it falls down, because you've given it enough momentum, enough speed, it will actually, as it falls down, it will carry with it some momentum, and it can actually start to orbit that planet. And so if you give it enough speed and you want to orbit something, it can become a satellite.
Yeah.
Okay. Now, you know what happens when they launch a rocket to go to the moon? Let's say to go to the moon. So we're gonna send people back to the moon. The last time we were there, were in the 1969 was the first one, right?
Yeah.
And since the Apollo 13 was unsuccessful because it didn't, tomorrow's Friday the 13th. So Apollo 13 did not make it into the moon. It actually went into the orbit, saw the moon, and then they had to come back, okay? And they were able to return. So you know what they did? So here is the Earth, and here is the moon, okay? So they tried to get this projectile into the moon. Do you think that we can actually just get a rocket and go to the moon in one flight?
Probably not.
No, there's not enough power, and also the Earth has such a very strong gravitational force, and it's pulling that rocket to the core. So what they do is they actually go around the planet once. They'll gain momentum as they go around. They're actually using the FG and not just getting pulled by it directly down. So they may actually go around and around, and every time they go around, you can look at, follow my pen here. So first they're following the orbit, and then every time they get momentum, it got actually more elliptical, like this, and then more elliptical, and then eventually they can escape the orbit of the Earth. So what you need, that when I talk about the enough speed, that enough speed is called the escape velocity. So you go fast enough, and you might be able to escape that orbit, or stay there if you'd like to, like the International Space Station, right? And it's no longer just going to crash land. Here's a good question for you. Do you think the space station, the International Space Station, is that falling into Earth? Like the Skylab back in 1978? Is that actually falling, do you think? You know the International Space Station, right?
Yeah.
This is a laboratory out in space where people of all nations can use and they collaborate for the progress of science, right?
Yeah.
This is that one place where the boundaries dissolve, and people who are typically not getting along on Earth, they can work together in peace out there in that ISS. That's the hope, and that was the plan.
Falling to Earth, but it will take a long time.
So is it falling? Yes, it is. When I say falling into Earth, is it being pulled by the FG?
Yes.
Yes, it is. But why is it not crash landing like the moon? The moon is falling into Earth just like we are falling into the sun. That's what FG is. Look, this is what FG is. That core to core, that big arrow, that's the FG. We are being pulled by it. Why is the moon not crash landing to Earth? Why is the ISS not crash landing to Earth?
Because there's enough centrifugal force to keep it going.
Yeah. Okay. Let's explore that for a second. You see the big arrow there?
Yeah.
What do you need to do so that this arrow becomes balanced by something else?
There has to be another force pulling against it.
Arrow has to go somewhere. There has to be another force, right?
Yeah.
So in order to get a net force of zero, this is a state of equilibrium, the FG must be balanced by another force. Do you agree?
Yes.
Read that sentence again. Now, you just wrote the test on dynamics. You know that in order for a net force to be zero, you must have two forces that are paired up and are balancing each other, right? Put your hands together like this, okay? And just make it 90 degrees, your hand 90 degrees with your forearm, and just go like that, okay? Bend your wrist and push as hard as you can. Push as hard as you can. This is a good workout, right? So if you are pushing as hard as you can and you're not going to the left or to the right, what does that tell you?
That the forces are equal.
That the force of your right hand pushing that way and the force of your left hand pushing to the right must be equal, and in opposite direction your net force is equal to
Zero.
zero. You are in a state of equilibrium. Now what if, let's say, alright, so my left arm hurts, or my left part of my body is hurt, and you're starting to show some signs of imbalance, so that's no longer equilibrium. One of the tests that you could do is, well, you can raise your hand, right? If you can't do that anymore, if you're going like this, and the other one just won't raise anymore, you could do this as well. And if you're going like that or going like this, that means something is going on in your body, and that would be a cause of concern. So if you could do this before a net force of zero, and all of a sudden you're going like that, you're weak. There's weakness in your left, and that could be a sign of a stroke, aneurysm, or a heart attack, when you're no longer in a state of equilibrium when you used to be. Okay? That's a good test that you can do. And it's also a good exercise, by the way, for your pectoralis muscles and your shoulders. Just that's it. You're sitting down, you're doing that, and you're doing this. You're exercising. Okay, so let me get a bicycle wheel. Albert Einstein once quoted that life is like riding a bicycle. Life is like riding a bicycle. You need to keep pedaling to move forward and stay balanced. Now, is that true? He said that because he used to like riding a bicycle. Marie Curie and her husband also like riding bicycles. Riding a bike is so much fun. Okay? So here's a bicycle wheel, right? If I just let the bicycle wheel stay stationary, what would happen? You know what's going to happen?
It's going to fall over.
This is the center of gravity, the point of pivot right here, right? So it will want to pull the center of gravity to the center of gravity of the Earth. And that is what's going to happen, right? So Albert Einstein said, you want to balance this thing here? Because look, if I were to just hold it like that, I'm trying to balance this in midair. It doesn't. It doesn't balance. The only force acting is Fg.
Yeah.
Just like the moon. If the moon stops moving, right, like this bicycle, well, what's going to happen?
It's going to crash into
It's
Earth.
going to crash land into Earth. If the International Space Station slows down or stops moving, it's going to crash land into Earth because of that arrow, the Fg. And this is what happened to the Skylab back in the 1970s, is that they call it orbit decay. So the orbit basically started to slow down. It started to slow down because Fg kept pulling and pulling on this, and it didn't have enough momentum and motion to stay in orbit. It eventually crash landed. And good thing that the planet Earth is 3/4 or 75% water. So most of that lab landed in the Pacific or the Atlantic, as opposed to people who populated places. Okay, so here's what Albert Einstein said. If it's stationary, only Fg is working. Now I'm going to introduce a force, spinning force. And take a look at that. Isn't that neat?
Yeah.
Very simple phenomenon, and yet mind blown. All you need is, you cannot fight the Fg. That Fg will always be there. But what do you need to fight a strong, it's not strong by the way, it's a weakest of the four fundamental forces, but it's always dominant. You can never get out of a gravitational field, right? So to deal with that FG,
You need to be circling.
you need to have another force. And one of the forces that can balance that is another force. Is called, in that case, it's the spinning force, right?
Spinning force, yeah.
So what is balancing your body right now? How come you're not getting taken to the core of the earth? What's preventing you from being swallowed by the earth?
The ground, which is...
Well, you're not standing on the ground, are you?
No, we're standing on
You're sitting on the chair. What do you call that force? F of N. Okay, that is not action and reaction. Keep that in mind. That is not the action and reaction. I just want to clarify that. Where is my black pen? So this is you, your body. Let me see my black pen. So your body, this is you. You're sitting on that chair. This you already know. You just came out of that test on dynamics. Your Fn and your Fg, they are net force of 0 together, right? But you see here, this is not the action and reaction as stated in the third law of Isaac Newton's law of motion. This is not the action and reaction. This is just a paired force, and that's the heavy duty physics there. Most people think that because that's up and this is down, this is action and reaction. It's not, okay? What the real action and reaction here is that I'm going to draw the whole planet here. This is you right there. You are being pulled to the core by the Earth's mass. That's called the Fg. I'm going to call it the Fg action. So that's the action. The Earth is pulling you down. But you know what the real reaction is? Okay, so here it is. If the action force is Earth pulls the person, I would have called it body. Earth pulls person. The reaction force will be, read that sentence again. Earth pulls person. What's the opposite of that?
Something pushes the person.
Person pulls Earth. That is the true action and reaction here. So you're sitting on that chair. The chair is offering a surface force. That's the perpendicular. That's a perpendicular to the surface. That is just a paired force here. This is called paired. Paired forces. They are not action and reaction. The true reaction is the exact opposite of the action force. Okay, here's another scenario. Nick punches the wall. Action force. Tell me, what is the reaction force?
The wall punches me.
Exactly, exactly. You guys tried that. You try punching the wall.
It's gonna hurt.
Why would it hurt?
Because the...
Say it again, Nick.
Because, like, when you punch the wall is pushing up against your face.
That's it. No, I like the way you said it first.
Oh.
Nick punches the wall punches Nick. That is the true action and reaction force, okay? I lean on the wall leans on me. Do you get it? When you're talking about action and reaction, it has to be between the two objects that are in the system. Because if I look at you, the Earth, and the chair, and I say, yeah, right here, the Fg pulls you down, and then you say, but the chair pulls me up. But no, we're talking about you and the Earth here.
Yeah.
The chair is not even part of the problem, okay? So that is not the reaction force. The true action and reaction is that if the Earth is pulling me down, I'm actually pulling the Earth to my core. And guess what? These two are the exact same magnitude. You go, what? How is that the same amount? Well, let's take a look. What is the FG that the Earth is pulling on you?
It's 9.8.
Let's just say you have 100 kilograms times 9.8. You've got 980 newtons of Earth's mass pulling you down. But guess what? The Earth pulls you down with 980 newtons. You pull the Earth up with 980 newtons of force as well. But then you go, well, how could I be pulling the Earth? So this is the real reaction right there. That FG reaction is actually what you're doing. You're pulling the Earth up to your core with the exact same amount of 980 newtons if you're 100 kilograms of mass. Would you believe that? Now, all right, so if those two are exactly the same magnitude, why is it that if I step off a ledge or a cliff, it appears to me that I accelerate to the planet and the Earth barely, or actually it doesn't move, it doesn't appear to move? How come you fall down when I just told you that the Earth is falling down on your body at the same time that you're falling? So at free fall, during free fall, and I didn't want to say this during the dynamics unit yet, when you're falling, an object that is free falling, Earth is pulling you down, but at exactly the same amount of force you are pulling the Earth to you. You meet halfway. When I say halfway, it's not halfway in terms of distance, but halfway in terms of the amount of force.
So you would actually fall with not 980 newtons. You would fall with.
You're falling at 980 with 980 newtons of force, and the Earth is falling to your body at 980 newtons of force as well. Hard to believe, right? Let me elaborate on that. So you got a big mass, Earth, right? 5.98 times 10 to the 24 kilograms, and then there's you, tiny itty bitty mass, 100 kilogram. If I were to push you that way with the same force, so force applied. Which one do you think? I'm applying the same force, okay? So I push something, and here's an example here. I take something that's not gonna slide with a similar amount of friction. So if I take a big, you guys have okay, I'm gonna use that, and a tiny little washer, which I should have. Oh, here we go. They are pretty close to the same mu, okay? Oh, okay, this is actually lighter than the washer. So what do you think would happen if I push something that is heavier mass compared to something that is lighter mass? There you go, paper clip versus washer. And if I push them with the same amount of force, okay. Okay, I'm actually gonna do this on the edge of here, and you could kind of see. Let's do that over there. This is heavier than this, obviously, right? Here, there, the same amount of distance there. I'm gonna apply the same amount of force. See that?
Yeah.
Okay. Paper clip went so much farther away compared to the heavier metal. They're about the same. They're the same kind of metal, actually. So similar mu. Why is the lighter object flying much farther distance? So what can you say about the acceleration of the paper clip compared to the acceleration of the washer? Which one had a higher acceleration?
The paper clip had.
Right. Well, that's why it went farther, because the acceleration was greater, right? But it was the same force. It was the same amount of force. So this one will be the distance will be longer distance. Why? Less mass. So here's what's happening. Okay? So when you step off a chair, a table, for example, and you know that you're going to fall down into the earth, and the earth is not going to accelerate up on you. Why? because compared to the mass of the earth, the mass of you is so insignificant.
Yeah.
You're like a speck. Okay? So of course you're gonna be flying so much harder with so much farther because your acceleration is so much greater, even though the amount of force is the same. So I just told you the amount of force is the same. You are being pulled by the earth as much as you are pulling the earth towards you with the same amount of force, except that you're going to move a lot faster with a lot longer distance. So therefore, it appears that you're actually the one that's only falling. But the earth is also falling to you.
Just ever so slightly.
Does inertia also come
Well, inertia, that's right. The larger the mass, the larger the inertia. And inertia is all about mass. That's all it is. Bill Nye starts all his shows before with Bill Nye, the science guy, with inertia is a property of matter. Guys, you know what that is? Inertia is a property of matter. That means if your property is a big mass, then you also have a big inertia if you don't have to be moving. Okay, so inertia is just plain mass, whereas momentum has to do with the motion. You have to move to have momentum. Inertia, you could be completely at rest. So bigger mass of the earth, greater inertia. It's harder to move with 980 newtons. That's nothing. But to you, who's a tiny, tiny, tiny mass, it'll be easier to break the inertia and move with a longer distance. Okay? So, yeah. So you are falling, but the earth is also falling to you. It just barely moves. As a matter of fact, when I walk and I move my body that way, do you know that I actually push the earth backwards?
Okay.
Move this way. In order for me to move that way, it's just like if swimming would be a lot easier. So if I were to take, this is water, imagine this is water, not air, okay? In order for my body to swim in that direction, I need to take the water and push it backwards,
Yes.
right?
Yeah.
So when I swim that way, I actually push the water back. When I walk that way on this ground, I walk forward. I have to push the earth backwards. Now, you go, she's crazy. Is the earth really going to be pushed backwards?
With only 980 units?
It's a huge mass. So what happens, the effect of me trying to push the earth backwards is that the earth ends up not moving and I move forward. That is the effect of that. There's the physics of walking. I'm pushing the earth back with every step that I take. Except the mass is so big, the inertia is so huge, so the earth ends up pushing me forward.
It's like you think a wall, bounce off the wall just stays there.
Exactly, because of so much inertia, it's also to the ground, right? So if you punch somebody on their face just punch your fist back, and your fist will hurt. Okay, so you get in trouble and you get into a fight and say, I heard you, Tyler, you just punched. Look on the face, and then Tyler can technically argue that yes, that was the action, but his reaction was that his face punched my fist at who started it. Then he can actually argue that it happened at exactly the same time. He hit me back at exactly the same time, and then I'm gonna go, Tyler, no, seriously, who hit first? And you can actually, technically, with physics, argue that the moment I hit him, he hit me at exactly the same time. That is a true action and reaction. Okay?
Yep.
No, don't use that as an argument. That would be a criminal assault. Okay, so but in physics definition of action and reaction, that would be it. Okay, so now let's just summarize this intro. So in order for something to actually become a satellite, you start with the projectile motion. You just basically fire something along the horizontal, even if you just ignore the vertical, just the v1 of x. You give it enough velocity, it will become, that projectile becomes a satellite. What satellite is. So this is now rocket science we're getting into. And then once you have this will become, this now is orbiting. You see that? That is what's happening with the moon.
Yep.
So the moon actually now has what we call FC. FC is the centripetal force. Now, keep in mind, this is centripetal, because there is going to be another It's a pseudo force though, that we will take a look at before the end of today, that it will sound similar. So this is centripetal force. Centripetal force is going to balance the Fg. When that is the case, the net force is equal to
It's equal to 0.
0. And again, the bicycle, here's Einstein's bicycle. Think of him on Saturday. Think of him riding his bike. He was a ham. There's the most famous picture of him. A picture of him with his tongue sticking out and riding a bicycle. So there you go. Fc of spinning is now equal to the Fg and have a state of equilibrium. Yeah, and the moment you stop pedaling, your bike wants to go down, right? Same thing with the motorcycle. Motorcycle on 2 wheels. You see them stop at a red light, and they have to actually put their foot on the ground. Otherwise, their bike will go down because the only force will be Fg, and Fg always takes stuff to the center of the earth. So you need to use the Fc to balance that. So welcome to the uniform circular motion unit. The uniform circular motion, we call it uniform, so UCM, and this is what we're going to be covering in Physics 40S. We are not going to be dealing with the non-uniform circular motion, and you only deal with that in engineering, okay? Not even in first year fundamental physics. So uniform circular motion, that means that the motion of an object going around something is uniform. What does the word uniform mean?
It's the same.
The same what?
It's the same force all
It's
the way around.
maintaining the same force. That's right. Very good definition. It's just maintaining the same amount of force. And of course, the mass will be the same, so it will be the same distance, and it will be the same acceleration as well. Okay? So that's what we're going to be dealing with. So some vocabulary here. What does uniform circular motion mean? So this is dealing with now objects that go around a fixed point. It can also be dealing with objects that are orbiting a central body. So we're going to be dealing with two kinds of spinning things, objects that are going around in circles. I brought a toy and I borrowed it from my kid. There's always something that you can. So I'm going to show you this thing here. You guys seen this toy? This is really cool. Okay, so this thing here, this is a top. It's a gyroscope. And this is one of my favorite toys when I was a kid, gyroscope. So when I do this, there's actually some mechanism inside that will rewind, that will wind up, and then it spins. So there's an example of UCM right there. Uniform circular motion. So, which one's gonna win? Of course, I did the orange first, right? Have you guys seen, there's a game, it's called Beyblade?
Yeah.
Yeah, Beyblade is a demonstration of UCM. And you have this bowl, right? Of course, this one ran out first because it was done first, right? Fascinating. So that is one example of UCM where it's just spinning around itself at one point of axis, right? Earth is doing that.
Yeah.
How long does it take for Earth to do one full circle?
24
Like go
hours.
once around. 24 hours, right? One day. Now, we know that the Earth is doing that. It takes 1 day to do that. But if this is the sun, 150 million miles away, what is that? 2.0 times 10 to the 30 meters. Okay? So this thing going around once 1 day. But while it's doing that, it's also going around the sun, right?
Yeah.
Okay, so what is 1 year? That's 1 year.
Yeah.
So if I ask you, is Emma celebrating a birthday soon? And then you go, well, how many times have you been around the sun? What am I asking? I always ask this when I ask somebody what is their birthday. How many times have you been around the sun, or how many revolutions have you done?
Yes, no, we are.
Yeah, that's what I'm asking. That's what I'm asking. Because if you go around once, that's 1 year. So now, answer this in your head. How many times have you gone around the sun? That's a cool way to ask, don't you think? How many times have you gone around the sun? It's saying, how many years have you done?
Almost 34.
There you go. So that's that. Also, an example of UCM is getting something on a string, and I just had a string, I just cut this one here. I could also be a fixed point. I can have a pendulum. A pendulum is just a string with a mass that is hanging, okay? So I could also do this. So this is also an example of uniform circular motion, okay? So I'm the fixed axis, I'm a fixed point, and objects going around the fixed point. This is uniform circular motion. Or you could be no strings attached, orbiting a central body, like the Earth going around the Sun, the Moon going around the Earth, solar system going around the Milky Way, and the Milky Way going around, who knows? That is all uniform circular motion.
How long does it take the moon to travel around the Earth?
For which one?
The moon to travel
The
around the
moon?
Earth?
About 27 days.
Oh, okay.
Yeah, 1 month.
Okay.
1 month. And then how long does it take for the Milky Way? How long does it take for us to go around the Milky Way? So this is the Milky Way, our spiral galaxy. We are right around here, third into it. Let's say that I want to go from end to end, from here, point A, to point B. Say I want to go and have lunch with my friend who lives on the other side of the Milky Way. I have two choices. I can go around, or I can risk going through that black hole. I don't know. Let's say I do. Go around the black hole and meet my friend on the other side and hitchhike in the galaxy.
Yeah.
You know how long it will take me? At the fastest possible time, speed of light, from here to here. Make guess? How long? This is the Milky Way.
Isn't it something like so many trillions of years?
100,000 light years away, which means at the speed of light, it will take me 100,000 years to go end to end of our Milky Way alone. Of course, that's gonna get sucked into that black hole. But yeah, if you go straight in the shortest possible path, then you go. So if you want to say hi to, if there's other life forms somewhere else in our galaxy alone, there are billions of galaxies out there that we know. Okay, so if I were to just look for intelligent being from here to here, and I sent a message at the speed of light, I texted my friend who lives in B, and I say hello out there. 100,000 years later, my friend will say hello back. That's 200,000 years have passed. Right? The person that has started the research, way long gone.
Yep.
Long gone, right? So is it possible to communicate with other intelligent beings on Earth? Not with this kind of physics,
No.
right?
No.
With classical mechanics, and we say, yeah, we can calculate this V equals D over T, so the T equals D over V. So then I know that if the V is 3 times 10 to the power of 8 meters per second, which is the speed of light, call it celeritas, then I know my V, and let's say that I know the I know the distance. We can do mass spectroscopy or do all kinds of stuff. There's a star right here. We can calculate the wavelength of light, and then I can then figure out how long it will take to go from there to there, and hence we got 100,000 years.
Yeah.
So that is if the Earth, if the space is linear.
Yeah.
Okay, but what if the space is actually curved? What if the space is curved like this? All of a sudden, A going from A to B is
Really close.
like that.
Yeah. Actually, that's where scientists are talking about
Seconds.
being able to be able to do is to be able to fold space, because that
Just
would actually,
find a place in space where space is curved.
yeah.
So now that's getting us into the unit that will be the relativity. Okay, that's what Einstein said anyway. So look at that. I got from A to B in a matter of seconds, whereas it will take me 100,000 years at the fastest possible flight. Okay? Because of another kind of thinking, another kind of physics.
Would it be a lot faster?
Mhm.
Back to that sheet, would it be faster to go, get to the center of the galaxy? Because, as more of those places, at the center, there's more mass, so,
Mhm.
space is
Yeah.
curved even deeper, so shouldn't it be, shouldn't you be able to,
There's a black hole right here.
yeah.
So the FG is so strong, right?
Yeah.
So
Hide that.
you can just ride that. You can just fall into it. But you got to remember, you're also spinning. Yeah, you're also spinning, so you can't stop that spinning. The only way you could actually just ride that FG is you stop spinning. But you see, things are spinning already. The planet was already spinning. Now you go, well, why is the Earth even spinning? Why is the moon going around the Earth, right? All these things are good questions to ask. Who or what started that motion?
We don't know about the speed and the start of the motion, but we do believe that the moon broke off the Earth
Yeah.
so many